freeway at a constant speed, and I pass a stationary car, well, there's no way for me to know, am I going down the freeway at a specific speed, or is that person moving backwards at a specific speed? Obviously, we could look at the tires and the scenery, right? But that's all using some other external reference, right? You imagine if I subtract out all that, right? Use the example of spaceships in space again. If my spaceship is moving this way and someone else's spaceship is standing still, well, if our engines aren't firing, if I'm just coasting, I don't know who's moving and who's not, right? Okay. So, but now we're doing this calculation from the perspective of the person who's on the Earth, the person who thinks that they are standing still, right? So this distance here, again, is the velocity of that ship that we observe and 1/2 of a tick that we observe. Then, of course, if I wanted to know this full distance that the light travels over 1 tick, well, I just use Pythagoras' theorem, right? So this distance here is going to be square root L0 squared plus 1/2, plus 1/2 v t naught squared square root. Okay. Now keep in mind that this is for a 1/2 tick. So if we want the distance in 1 full tick, that is going to be 2 square root L0 squared plus 1/2 vt squared. Okay. So this is the total amount of distance that light pulse has moved from the perspective of the unmoving observer. Okay? But we haven't used the speed of light c. So obviously the simpler way to find this number is to multiply the speed of light by how many ticks we observe, and that's how far the speed of light has moved. So in 1 tick, this moves c, the speed of light. So c t naught. So these two things are equal, right? This distance measured here is equal to the speed that thing is moving at times how many ticks we see. So far, so good. But, as I was saying a little bit ago, from the moving person's perspective, they're standing still, and we're moving. So if they're in their spaceship with their light clock, they don't see their light clock following this diagonal trajectory, they just see their light pulse moving back up and down. If they looked at our light clock, they would see that sawtooth trajectory in the opposite direction, but they, on their spaceship, just see it bouncing straight up and down like this. So the distance they observe is L0. Okay? And from their perspective, this is c times ts divided by 2. The 2 is because this L0 is a 1/2 tick. It would be for 1 full tick, I'd have 2L. So this distance, L0, the speed of light from their perspective times the ticks that we would see them undergo. Okay, so let's be careful about what this TS means. This TS means that the number of ticks that the stationary observer on the Earth sees the moving light clock undergo. So from the perspective of the person on the ship, their light clock is ticking normally, right, at that same rate TS that we observe. And times c divided by 2 gives us this L0. Okay? So there are essentially 2 ways to calculate this distance. 1, from the unmoving person's perspective on Earth, and 2, from the moving person's perspective, who thinks they are not moving, in their spaceship. Right? The difference is which time we use. Right? In this formula, we use T0, the observer's opinion about how their own clock is ticking, and this TS, the stationary observer's opinion about how the moving clock is ticking. And the reason we can use both of these equations to mean the same thing is that, and this is, I'm going to put a star because this is really important, the speed of light, c, of course, is same for all observers. Okay. So there's two essentially postulates of special relativity. One is that if you're in motion at a constant velocity, there's no experiment you can perform to prove that you're in motion, right? Which we are used to from the idea of Galilean relativity for non-inertial, that is non-accelerating observers. And the second postulate is that the speed of light is the same for all observers, right? So I get this equation, right, with this same c, because from the moving person's perspective, they see the same speed of light as the stationary person sees. Okay. So what we're going to do now is take this new definition for L naught and plug it into this equation over here, right? We want something that relates the times that are observed between these two clocks. So we're going to eliminate this L naught. I'm going to erase for a bit. Okay. So we equate those two equations that we had on the previous board, and we get, or rather we sub in that that L naught. I'll just do both steps. So this was from the previous board. L naught squared plus, I always forget this, 1/2 v t naught squared equals c t naught. And then we sub in that L naught that we had on the previous board. So we've got 2 square root c squared ts squared 4 plus v squared t naught squared divided by 4, right, where we're doing this, this square there, equal c t naught. All right, and then of course I can bring both of those 4's out front and cancel with 2, and then I'll square both sides. So we get c squared ts squared plus v squared t naught squared equals c squared t naught squared. And then doing a couple lines of algebra, ts squared equals t naught squared minus v squared divided by c squared t naught squared. So I'm isolating my t's, right? I divide by this c squared and rearrange. And then I can just take the square root and I get ts equals t naught square root 1 minus v over c squared. Okay. So this is sort of the central result of this lecture, the central result of time dilation in special relativity. Time dilation. It's possible that's how you spell dilation, but I'm not sure. Okay. So what does this equation mean? Well, it means that the number of ticks we see the light clock ticking on the spaceship is equal to the light number of ticks we see in our clock times this factor here, which is dependent upon the velocity. Okay? So if I take velocity equals to 0, well then this term is 0. I have 1 minus 0. I have square root of 1 is 1. I have ts equals t naught. Nothing funny is going on. Okay. What if I make that velocity bigger and bigger and bigger and bigger? Well, this number, right, as that velocity gets close to the speed of light, this number becomes bigger, closer to 1. As this number gets closer to 1, well, 1 minus a number that gets close to 1 is a small number. I take the square root, and then I multiply that by the number of ticks the observer on Earth has for their clock, and I get some smaller number of ticks for the observer in motion. Okay, so that means that what's happening is the observer in motion, right, I see their clock ticking more slowly than my own clock. Okay, that might not seem weird at first until you think about it for a little bit. This is a clock that's defined on a natural process, the propagation of light, right? Other physical processes would yield the same results, right? If I had built a clock based on some other interaction, right? That would be based on the same physical mechanical laws as my light clock. So no matter what process is taking place on that spaceship in motion, it slows down from my perspective as I see the velocity of that person increasing. So it's not just that their light clock is ticking more slowly, their regular clocks are ticking more slowly, right? The computers that run in their spaceship, you can imagine you could build a computer out of optical devices. It's an active area of research, right? And maybe they have an optical computer on their ship, and that also runs slower. And the same thing would happen if they had an electronic computer. The same thing happens with the biological processes that take place inside their bodies. They all run at a slower rate merely because that person is in motion. Okay? Which maybe that seems a little strange, but it gets even stranger. And it gets stranger because remember one of those postulates I mentioned, right? That if an observer is in motion at a constant velocity, there's no way for them to know if they're moving or not, right? If you're in motion and you see someone else stationary, you feel like you're stationary and they're moving, as long as neither of you are accelerating, okay? So what that means is that if I did this whole analysis, but switched the perspectives, right? Now I imagine that I'm on this spaceship, I see a person on the Earth zooming past, I could do the same exact calculation, right? And it would look to me on my spaceship like everything was going slower on the Earth. What does that mean? It means there is no absolute notion of time. Time is intrinsically a relative phenomenon, right? In order for us to talk about how much time has passed, we need to know how much velocity we're talking about. We need to know if we're in motion. So there is no absolute notion of time, only a relative notion of time, just like there is no absolute velocity. There's only relative notions of velocity. So time is relative, everything you believe is a lie, etc., etc. Okay, so that's kind of interesting, hopefully. One thing I want to mention is this should drive home the point that you can't use your common sense or intuition to reason about the world. It works up into a point, especially if you're thinking about things that are very familiar. But that doesn't mean that's what reality is, right? Reality is always something stranger and more complicated than you think it is. So always question your beliefs, always take new information into account, always think through things carefully, and if you can, mathematically, right? It's this certitude that things work a certain way that gets us into trouble, right? And so this should demonstrate by its very counterintuitive nature, right, and the provable truth of this, that we can't make assumptions, right? We can't use our common sense. We have to think deeply about everything, even the nature of time, okay? Which perhaps at the beginning of this lecture seemed very intuitive to you. Okay, so the next question might be, okay, A, why don't I see clocks ticking at different rates if they're moving around? And B, is this really true? Can we prove this? Well, okay, first question first. Let's take some numbers so we can get our heads around this a little better. So, I thought I had this written down. I just wrote down the number, but I think I got it from somewhere. So I think this is true, but I'm not certain. So let's take a velocity, 1,000 meters per second. And I think where I got this number is it's roughly the speed of the SR-71 Blackbird spy plane, so the fastest plane that's ever been built. I think that's where I got this number, but I could be wrong. Anyway, this is roughly the fastest any human being has gone on the Earth. Okay. So what happens if we plug in 1,000 meters per second into this equation here? Well, we've got this V over C. So V over C, I've got 1,000 divided by roughly 3 times 10 to the 8th. And then this is 1/3 times 10 to the negative 5. Okay, and then I take the square root of 1 minus the square of that number, and I get something roughly 0.00000, or right, no, sorry. 1 minus 0.0000003 squared. Okay, so this number becomes 0.00000000009. I subtract that from 1. I take the square root, I get basically just 1. Okay, with only a very, very small variation. Okay, so even traveling the fastest that any human being has ever traveled, that's still nothing compared to the speed of light. So I can't really see this effect. It's too slow for me to see this time dilation effect. Okay, how about if we think we're moving at half the speed of light, which is very fast. So if we say v equals 0.5 c, right? Obviously then v over c is 0.5, and then going down here, square root 1 minus 0.25, which is 0.5 squared. This is about 0.9. Okay, so now we can see a small effect. This is a little bit different from 1, 0.9. So you plug that into here, and that would mean that if we have 10 ticks or 10 seconds pass for the observer on Earth, 9 ticks pass, or 9 seconds pass for the person on the spaceship. We observe them to lag behind a second, right? And of course, if we did this the other way around, right, if we switch these definitions, then the person on the spaceship, if they experience 10 ticks, would see the person on the Earth experience 9 ticks. Okay, so this is why we don't observe this effect in our daily lives, because it's so difficult to see that we never notice it. Now, if we have a lot of scientific equipment, we can notice it, which brings us to the second question: can I really be sure that any of this is true? Okay, so I can be sure that this is true because people have done experiments with very sensitive clocks. Remember at the beginning of the semester when we were talking about measures and metrics and stuff like that, that the way that we can measure the passage of time very accurately is with a cesium atomic clock, right? That can tick out very, very small ticks on essentially the vibrations of a cesium atom. So what was done, the experiment that was done to demonstrate special relativity, people had really good reasons for believing it before that, but an experiment they did to show special relativity is they took a pair of atomic clocks, they kept one stationary, right? They calibrated the other one to it, and then they took that second atomic clock that was calibrated to the first atomic clock, and they flew it around on airplanes for a long time. They actually bought commercial airline tickets and put the atomic clock in the seat and flew it around the planet for however long. And when they brought those two atomic clocks back into contact, what they saw was that the atomic clock that had been in motion that entire time lagged behind by the exact predicted amount due to time dilation and special relativity. And there's lots of other effects that are a little bit more difficult to explain that show us that this is definitely the way that time operates. As strange as it may be, we have to accept it because the logic of the mathematics and also the experiments that have confirmed it time and time again. So all this stuff gives rise to something called the twin paradox. Right? What's the twin paradox? Well, again, let's imagine we're here on the Earth. Right? Okay, so this is you. This is you on the Earth. Okay, and you've got your own little clock here, and you're measuring time. And your twin is an astronaut. They're much better achieving than you are. You've wasted your career, and now you're stuck in Ohio or something. but your twin's been very successful and he's gone off on a spaceship in outer space. Okay. So you would think, well, I'm going to stay here on the Earth, and my twin's going to go off into space, fly at some really high velocity for many years, and then come back from some distant planets. When we get back together, who's going to be older? Okay, you know, all this stuff I've been saying that you can't tell the difference and time is relative. Well, if that person flies off and then comes back, won't they look younger from my perspective and all look younger from their perspective? Maybe. So that's the twin paradox. Who's younger or older after one twin goes off into space, goes to some distant star, and comes back? Okay, so I would, again, if we were here in person, I would say, okay, who can tell me why this situation is different from the one we've been discussing? And so pause, think. The difference is acceleration. Okay? Everything we've been saying for special relativity is for the special case of constant velocities, right? We always talked about inertial reference frames with no acceleration. It turns out that when we introduce acceleration into this analysis, that's what breaks that symmetry, right? Because if you think, I'm sitting here on the Earth, I never go anywhere, I never need to accelerate. My twin has got to blast off in this rocket, accelerate really fast to get to this distant star, and then he's got to decelerate and stop and hang out at the star for a little while, hang out with the green aliens or whatever, accelerate back up, come back this way, and then decelerate again, right? When that process of acceleration is taking place, it's in a sense recorrecting those times, right? So my twin, because he or she's the one that's been accelerating, they're the one who comes back younger than I will. Okay, so that acceleration, deceleration rectifies that disconnect between those two possibilities. Okay, so I mean I've gone over a little bit of time. This is obviously a really deep subject. I encourage you to go watch some more videos or some great YouTube videos on relativity. You know, do your own research and reading. It's a really neat subject. If you really want to dig into it more, the next things I recommend you look into are Lorentz contraction and maybe the barn and ladder paradox. Do this one first because this one you need these concepts for this. So briefly, the question is carrying these ideas to the logical conclusions, where in fact it's not just time that changes when we go at high velocity; it's also length, right? If I had a standard ruler and I made that move really fast, from the stationary perspective, it would look like it would shrink. Okay, so you know, lots of weird stuff tied up in this, and I encourage you to go do your own research because it is pretty cool. Okay, so hopefully this was an interesting break from our regular sequence of lectures and figuring out whether the block tips over and how fast the thing is going when it gets to the end of the inclined plane, and et cetera, et cetera, et cetera. Okay, so again, I will give you a practice exam on Friday, and that will be the lesson for that day, doing that exam. Monday will be the real exam. And then when we pick back up with lectures, we'll start to cover our final topic, which will be oscillations and waves, and that will be the last thing we do in the semester, right? And so that topic will be tested for only on the final exam, okay? Oh, and one more thing. So in the syllabus, it says that everyone who gets an A on all 3 in-class exams is exempt from the final. I intend to honor that. Usually what I do is have those students who have gotten all 3 A's to get out of the final, they do a presentation or something like that. I will most likely still give you some sort of task like that, maybe to write a short paper of a page or 2 on some advance in physics or something like that. So that option will still be out there if you get you know, an A on this next exam and you've gotten all A's on the previous 2, then you will have at least the option to be exempt from the final via some mechanism, and I'm not sure yet what that mechanism is. Okay, so all of you, I hope, study hard for the exam. Again, practice exam on Friday. Hope you're all staying safe and healthy. All the best.